So looking at problems involving lifts, this is not just about lifts, it's about any particles that are connected by one thing being on top of the other. So there's some good examples in the textbook, and I would recommend that you have a look at them, where we've got scale pans and different particles being added to the scale pan, and it really does help with the understanding. Now when we look at the forces that are acting on a particle, we don't really consider the surface that that particle is resting on, whether it's a car, whether it's a book on a table. We're just looking at the forces that are acting on that particle. Here, because the whole system is going to move, so it is the floor of the lift is also moving, so the surface that this person is stood on, then we need to consider the forces of the lift separately to the person. We also need to be able to put the whole system together. So I'm going to start this at the right, so I'm going to look at the person first. So the person is stood on the floor of the lift. The forces acting on the person, well, there's the weight of the person, but also there is a reaction force. Don't know why the reaction force is coming straight out of their head, but there it is. And that force is the force exerted by the lift on the person, the force exerted by the lift on the person. Because when the lift sets off, so if you think about it, when the lift goes upwards, then it's the floor that's pushing that person upwards, and that is the force is being exerted on the person in order to move that person. If we consider the lift, and this is the lift, not empty, but with the person in, okay? So we'll just add that in. So this is the lift with the person in, but what I want to consider are the forces that are acting on just the lift in this situation where we've got the whole system. So first of all, I've got a piece of string at the top. Well, not a piece of string because that probably wouldn't work very well, but we do have that wire at the top, and therefore we have a tension that is pulling the lift upwards. If the lift is moving downwards, then it is that tension that is stopping the lift from falling. We also have a weight of the lift. Now, if the person is stood in the lift, it's easy to think that there is the weight of the person acting down on the floor of the lift, but it's not actually the weight of the person. It is the reaction. So this R is the force exerted by the person on the lift, and it is equal to the reaction that we saw with the person. So the force exerted by the lift on the person and the force exerted by the person on the lift is the same force. And the way to think about this, it is quite hard to get your head around. The way to think about this is if the lift is stationary, R over here, if I was doing F equals ma, so if we've got acceleration is equal to 0, then R would be equal to WP. So when that person climbs into the lift, R is equal to the weight of the person. The reason why it's not the weight of the person all the time, just think about if you've been on Tower of Terror or at Disney, the ride where the lift drops, or Ice Blast, is that what it's called now? Blackpool. So any of those rides, just think, go to the extreme system. So when the ride is at the top and it drops, there is a moment where you leave the seat, and that either is a thing that makes you feel sick or it's the thing that you enjoy, which is why you're on the ride in the first place. But it's that connection between the surface and the person that is this reaction force. So that will change that idea of weightlessness, I suppose. The weight of the person in that situation of being dropped, so if the lift breaks and that lift drops, the weight of the person is not going to change. Therefore, we cannot claim that this force here is equal to the weight of the person, because as the lift moves up and down, that force will change. And normally what I would say at this point is when you leave the lesson and you get in the lift, just have a think about those forces and see if you can. It'll only be slight when you're in the lift at college, because hopefully it's not going to break. But you will feel that those forces are there. Okay, so when you get back into college, which hopefully will be soon, think about that force and it should help you to understand what's going on. Now, when we plug these together, so the weight, if I put the person's forces into here, so there's that reaction force for the person, and then there's the weight of the person. If we consider the forces that we have for the lift, we've got tension, and we've got weight of lift, and then we've got this reaction. So actually, when I am doing the whole system, I don't need to put this reaction in, because they cancel each other out, because one is pointing upwards and one is pointing downwards, and they're equal and opposite using Newton's third law of motion. It will take a while to get your head around some of this, just working out which force is which, and we will do a lot more practice on these types of questions, just to give you a little bit of idea of what is going on. And it's about focusing on which force acts on which particle, and in this situation we need to also consider the surface as well as the person that is inside. Let's have a look at the example. So looking at example 2.5.3 and applying the information that we've just talked about with lifts to this question. So we've got a woman of mass 60 kilograms is in a lift accelerating upwards at a rate of 2 meters per second squared. What I should have said when we were looking at the last section is the acceleration of the person in the lift is going to be exactly the same as you would expect. In this question, find the magnitude of the normal reaction of the floor of the lift on the woman. That will take a few times reading through. So the normal reaction is that upwards force when we have a particle connected with a surface. So the normal reaction of the floor on the woman is the force exerted by the floor or by the lift onto that person. So if we are considering our diagram, I am interested in the person diagram. So we have got a weight of 60g, don't judge the artwork, and we've got a reaction, and it's that reaction that I'm looking for. The lift is moving upwards with an acceleration of 2, therefore the person must be moving upwards with an acceleration of 2. So doing our calculations, we're moving in an upwards direction. The force in that direction is R. Take away any force against the motion, which is the person's weight, is equal to mass times acceleration. So when we calculate that, remember G is 9.8, so I get 708 newtons, but because I have used 9.8, I'm going to give that to two significant figures. If you were asked to find the magnitude of the force exerted by the person on the lift, this working out would do, because if you remember what we said, there is, if we're looking at the lift, there is an equal and opposite force that R, so that would be, so sometimes you get in a question where it says the magnitude of the force exerted by the person on the lift is the same as by the lift on the person. So you can use this person system, just because we don't know the tension, we weren't given any information about the tension or the weight of the lift, so I wouldn't be able to calculate anything using that system, therefore I would need to use the person system. And the same, I wouldn't be able to use the whole system because I don't know the weight of the lift and I don't know the tension, so it's very much dependent on which question, which information you're given in your question. This bit moves at constant speed, you need to cross it out, because if it's moving at constant speed we haven't got an acceleration, so we're just going to ignore that. So then the lift begins to descend. It's a fun ride. She must have gone to the wrong floor. So we are descending this time, and again we've got an acceleration. This time motion is down. The weight is the same, but the reaction will have changed. And again, it's that idea, is if the lift went really fast, then there would be a loss of contact with the floor, and that's kind of what's happening. So we're expecting R to be smaller than it was in the first situation where the lift was going upwards. Okay, so we're expecting it the other way. So because I'm going downwards, F equals ma, the force in the direction of motion is weight. The force against motion is R, is equal to mass times acceleration. So then when we calculate R here, we get 498. And therefore, because I've used G, if I give this to two significant figures, it is 500. Okay, so we get 500 newtons in that situation.